Okay, next speaker is Jens. We're all set up. And,
okay, thanks, Greg. And I'm really happy to be here in the community. Thanks again to the conveners to set this up. Yeah, I'm talking here with a of two teams. That's on the left side in the west of northern Germany. That's a Kiel team from the Marine Geophysics and Hydroacoustics group at Kiel University. And on the east, which you cannot see, on the right side on the previous slide, there's the team from Rostock, also in northern Germany. Yeah.
Just drag that bar.
Yeah, and those two teams, these are around about 10 people, which you can't see now. Very good.
let's do it again.
You stop the time.
I stopped the timer.
All right, team hasn't changed. Still the same people on the right side, the guys from Rostock. And we're working a lot on the German research fleets, what you see here, but also employ our small survey boats, mainly in the Baltic Sea and in the North Sea, but also on global scale on some research expeditions. Well, our habitats that we are looking at varies, for instance, sea grass meadows, upgrounds, or these little worms that cause some peculiar backscatter. We also look at anthropogenic ways or imprints on the seabed, like cables or gas released from the seabed. And the good news is that we can sense all these habitats, natural and anthropogenic, with acoustic methods and also with optical methods. For instance, these little worms you only can see with laser optics that you can install on the seabed, for instance, with super high resolution. Well, we are using mainly multi-beam echo sounders, but also sediment profilers and SPL ROV for exact ground truth, which is very crucial. Also side-scan sonars. My colleagues are very much working with streamer seismics. We a little bit use lasers and subcontracted airborne laser overflights and dig a little bit into airborne imagery. And like to use customized approaches, customized processes. Yeah, in the last years, we used a lot of different systems. Many Kongsberg systems on the German research fleets, but also ELAC systems. Many don't know. ELAC is a multi-beam echo sounder located in Kiel, and I spent half my PhD in that company. And nowadays, we're working a lot with Norbit systems, and a little bit also with Kongsberg and Archsonic. And I hope it suits your demands. The Norbit was calibrated in a test tank by Halifax in Norway. And used in the project. So to put on the label, our work is basically experimental hydroacoustics. Some years ago, I started a large research development project that I was coordinating. That's EcoMap, optoacoustic remote sensing, mapping and monitoring of the seabed, especially in the Baltic Sea. And the claim was a little bit that the manufacturers have a little bit a static view of the seabed, like you have your measuring platform, the medium, and the target. But we all know the reality is different. The question was, how is the interaction with optic sensors and acoustic sensors? And the team was set up with colleagues from University of Feldens, that's Jaroslav Galowski and his team, and EOMAP, that's a spin-off from DLR, doing airborne as satellite-derived telemetry, and we have Norbit and Inma as the research development partners in the team. Well, this brings me to the first question. Questions of this workshop, and the questions are really well chosen. What are the state-of-the-art backscatter research? And we are talking about backscatter and watercolor issues. We are in multispectral, and I want to raise attention to two data domains that maybe they deserve more attention. That's multi-detect ME, I have here the short, and point cloud analytics. And a little bit also we might want to dig into optical approaches like LiDAR or airborne satellite hyperspectral imagery. Well, to verify multi-detect is nothing new. We employed this 15 years ago. Actually, this was my first scientific paper, so to say. Exploiting multi-detect echoes from an ELAC system. The basic principle is really straightforward. You send out a beam and you receive a time series. And the time series has some anomalies caused by, for instance, some fish. And time series, you do get the echo from the seabed, and someone has to decide in between what are the signals and who's the seabed. So is this the seabed or is this signal the seabed, and the decision is made by the bottom detection algorithm. And it's as simple as that. The bottom detection algorithm can throw one solution when you have one sounding of the seabed, or it can throw multiple solutions when you have several. That's usually encoded in the multi-beam files. Nowadays, also the Kongsberg has multi-detect and SFK. You can store these data, and it can be considered like compressed watercode. It's not the full tracks, but it can give you some indications what you need. And actually, in LiDAR, this technique applies exactly the same. When you're processing multi-beam, you're able to process LiDAR. That's angle travel time data. Well, we took this approach a little bit further and have a look at the sketch. So it sounds and zonified towards the seabed. And if you have a vegetated seabed of sea plus kelp or so, we can expect the first returns from the top of the canopy. And then the sound is being transmitted through the vegetation. If it's transferable to sound, then you get a second return and maybe a third return. Situation is pretty different when you have an obstacle with a shadow, and situation is different when you have the seabed itself. So the pure sounding distribution is kind of indicative of how the seabed is looking on a very, very small scale. And this can be exploited, so to say. So looking at that point cloud, fitting a surface through such a point cloud is not really meaningful. But this is what we do when we generate digital terrain models. I mean, it's straightforward and it works in many places. But you do have information loss, and you have sometimes falsification. In that case, if you draw a surface through, it's a falsification of the situation of the seabed. And you only get one surface, and it's blind filtering that we often apply. It's totally failing in that situation. So there are other approaches, for instance, point cloud analytics, and the techniques originate from astronomy, where you actually take one sounding and you have a look into the neighborhood. And you look how the neighborhood is distributed, and the distribution can be more linearly, more planar, like the seabed, or more spherical, like when you have vegetation. Well, you would expect it to be spherically aligned. And that's what you can exploit. And in some cases, it's closer to the physical reality, and it allows for 3D analysis. It allows for biomass estimates, and you can add computational expensive. That's the downside. Well, this brings me to some real-life examples. First example. It's in Canary Islands, some black corals on lava flows. That's the black coral, so it's built of chitin, so it's not very resistant. And it's sitting on top of a lava flow, very hammocky and very rough. And here we employed the multi-beam Norbit system with 400 kilohertz with a multi-detection mode. And we tried very many different modes. So we tried the snippet backscatter, we tried multispectral, we tried waterfall mesh, all failed. We couldn't see black corals, and the only data domain that succeeded was actually the multi-detecting echoes plotted here in bright blue. So don't be fooled by these colors. It's more a statistical approach. We run over by different survey lines, different angles, and realize, well, the multi-detect actually it's always appearing where the black corals are. So it gives you an indication where they are. So detection of corals, yes. Challenge, of course, that's no quantification, but it gives you a good hint where they might be. And this brings me to the geobioacoustic setting and interpretation. So I will show the example, the case studies on the left and the domains in the middle. And here the interpretation. And the interpretation is like the backscatter phase because the terrain is simply too rough. And we are at the edge of what's possible. Range resolution with between 60 and 80 meters. And considering you have a range resolution of 0.5% of the water depth, which is a good rule of thumb, then you end up with 0.35 meters vertical range. And black holes are about that. So the recommendation would be, well, this might be a good way to sense these, but it won't work at ranges larger than 1 meter. Another example, seagrass meadows. Well, it's well known that seagrass can be sensed acoustically. We also had an airborne overflight. Cannot be seen that good, but the dark patches are the seagrass on the sand. And well, when we run the multi-beam acoustics on top, it's a 100% match. It's really no doubt that we can sense even very loosely populated seagrass meadows when the survey conditions are good and the signal noise is fine. And we took that also further with a multispectral capability of Norbit. So what you see here is a pulse color composite of 190 kilohertz in one band, so red, and 370 kilohertz in the second band, and the third band. Constructed a difference, let's say a difference in between, and encoded to 8-bit. So the third channel gives you the difference. It clearly discriminates stones and sand, and also seagrass. Maybe unfortunate color here with the dark, but it really plots very clearly that you can discriminate the seagrass. So overall, we realized that all domains are pretty good. So you can see seagrass in backscatter, you can see it in watercolor, you can see it in multi-detect, but we found out that the best way to classify it is actually with point cloud analytics. We made a model, and the detection of seagrass, yes, but the model itself was better than 93%. So really very, very good. This is point cloud analytic, computationally expensive, but it provides you two surfaces, the blank surface and the one with vegetation. And the hydrographers, they hate vegetation because they need to get rid of it by manual editing, and that's very expensive to do so. So for them, it might be good to have ways to automatically delete them. Well, the challenge is a bit with the seasonality, and the reason why this happens with backscattering, we do have void spaces in the leaves, so it's a little bit like nest bubbles. We might have oxygen reduction on the leaves that deteriorates the situation because it will make the backscatter uncontrollable. You also have the acoustic cross section change to the currents back and forth. So all these lead to backscatter, and the angular range curves are kind of instated. So that's why we're saying we prefer the PCL Bucky soundings only. But you also have to keep in mind that we have airborne images and LiDAR systems around. And they perform down to 4 meters, and beyond we need the acoustics. So the recommendation would be choose a joint approach. Next slide. This is the situation. We have an overflight where you really can see the seagrass very clearly until the critical water depth, 4 meters. In LiDAR, you also see the vegetation by data gaps, but also by this anomalous point cloud. But we still have our acoustic niche in the opaque area where we need surveys to get a seamless map on seagrass. We're saying seamless map, that's the goal. That was one goal of the project. Well, we're coming to the next habitat that's important for our study site. That's simply our coarse-grained grape. Why the heck is that ecologically meaningful or important? Well, we don't have much of that, and many species need hard substrates. I'm not a biologist, but I was told it's really important. And the authorities who want to have methods that you can map out these substrates. And in that situation, we found that multispectral excels. Here in the image that you see again, it was reported with Norbit. This time with 3 frequencies, 400, 200, 400, and 700. False color composite, and similar as Dan has shown. Inken, our PhD or Peter's PhD, she has segmented their area to compile solid ARC curves. And you can see them here. The blue curve represents the high frequency 700 kilohertz, and that's plateauing on the gradient, and the 200 has a nice decay. And that's kind of what you expect in gravel, these differences. And that's what makes the multispectral so good to discriminate gravel against medium sand, fine sand. So probably it's very powerful to discriminate small grain sizes. What's the biogeoacoustic setting that's controlling this situation? Well, it's the outer range difference backscatter response between 700 kilohertz and 200 kilohertz. Well, the reason is the frequency is 400 kilohertz. We have a wavelength of 4 millimeters, where the size of gravels get, let's say, kind of interferential backscatter with omnidirectional scattering. At 400 kilohertz and at 200 situation is different from the scattering regime. That's why we have these large differences that we can make use of. Next, not an habitat, but rather a problem that we have in the Baltic Sea. It's two weeks ago, we surveyed seagrass here, and occasionally we find dump ammunition. In that case, it's probably a British ground mine, 2.5 to 6 meters long. And you can clearly see that in the backscatter image. It's only 5 meters deep, so the range resolution of the image is quite good. But when you sail across over this mine with the snippet imagery, I cannot see nothing. I cannot see anything. So totally disappeared. We all know that near side scan is not the best you can do, but I would have expected that that system, that survey situation, I mean, the data is pretty good. That we would have seen it, but we didn't. We don't know how this will look in the outer range. We will check soon. We don't know how this will plot in multispectral. So all the other domains we didn't check. I mean, we cannot check all domains everywhere because it would mean that we say every area 5 times that cost. At the current stage, it's a prototype. We cannot use all the nodes at the same time. But what's the acoustical interpretation? The geobioacoustic setting, like possibly the overgrowth. I'm not sure what that is. If it's red algae or it's something growing on top of it. If it's absorbing the acoustic energy, I don't know. Next domain is glacial hardgrons. I have to speed up a little bit. Glacial hardgrons, we found they are very good to be mapped with classical methods. Classical methods, I mean, multi-beam digital terrain model, because the slope is really good, and the backscatter doesn't work well. Once again, probably because of overgrowth or some other acoustic phenomenon, we don't know. We also found a peculiar setting in the North Sea. It's known that vertebrates stick into the seabed because they can sense with their sonar, especially whales, dig fishes in the seabed, and they sometimes dig into the seabed, leaving imprinting little holes, little pits in the seabed, which you cannot see inside. So the backscatter actually doesn't work, but only the bathymetry with its very high resolution provides you insight into such feeding habitats, in that case of whales, producing small tiny pits in the seabed. So the backscatter is useless in that case if you want to find it. So reason is no grain size variation. Depressions are shallower than 0.10 centimeters. Recommendation would be near range high frequency acoustic to detect it's a very special situation, but probably occurring on many places and be quite important. Last thing is shallow gas. So we struggle with that a lot. There was a lot of work going on by APL and naval research labs. Also in our place, here side. And if we have shallow gas in the seabed, we're in trouble. Ask Luciano, this is a PhD work. You can tell it causes huge volume backscattering. And this huge, you can of course sense the gas bombs coming out into the water column, but we are concerned with our multispectral, multibeam approaches that we are in trouble because we don't know how deep we go with our sound. This is an example where I used abused and deep water Kongsberg system 12 kilohertz. In 80 meters water depth, and the penetration was 12 meters. 12. On that side, here you see the color-coded backscatter, and then the bottom detection jumps onto the shallow gas front like half a meters below the seabed, producing this high backscatter here. So what about the acoustic penetration? Then we go with lower frequency, 50 kilohertz. Okay, with 50 kilohertz CDLAC system, I still found out at least 2 meters. And then you can produce these strange-looking rings. That's an acoustic artifact due to penetration when there's gas. Let's skip over that into time. Well, let's go higher with the frequency. Peter took this this penetration problem into a test tank in his lab, and they buried here gummy fruit gummies in mud and sandy mud, and then you can actually show that you can sense these down to 60 centimeter steps. I mean, it's of course a question of how much energy you send out, but it was not a very powerful transmitter. And even we had a survey with 300 kilohertz in very soft mud in the Baltic Sea, and we found out, together with the subatomic profiler, where we integrate over certain depths and correlate this with the multi-beam backscatter, that the multi-beam with 300 kilohertz picks up signals from probably 10 to 20 centimeters. That's a very soft mud. And also we have to clearly check for APL, there's a lot of work, gray literature in terms of penetration. Not yet. Well, we have seen multispectral which can show you pattern. And the pattern sometimes show a correlation with two frequencies, a negative correlation or a positive correlation, or the frequencies go in line. And it might be possible to construct indices with such phenomena, like in the terrestrial realm, like we have the DVI, vegetation index. And the question is, can we find indices that show the situation or indicate what's down in the seafloor? Is it micro roughness, bioflotation, biofilm sponge, microphytes, buried fish, and whatever is out there? We don't know. But possibly we can find in the future some indices being predicted. Well, second question, what do you see as a priority research area? Our claims, there's no one-fits-all solution for habitat mapping. And therefore we need to analyze which data domain is suitable for which habitat. We should go acquire spectral response of specific habitats and develop robust indices. That was also Xavier's recommendation to build up a spectral library back in the days in this talking alone. Investigate penetration depths for various frequencies, as you also have shown, Greg. That's an important goal. Determine depth boundary between optic and remote sensing and acoustics. Well, it's a little bit strong on our own sonar ACE, but the optical methods really are very useful in the what I call coastal white ribbon, because it makes no sense to survey those acoustic systems that shallow. Overcome range dependencies, that's probably another topic, could be solved by AMVs and SAS systems. Well, this brings me to Xavier's recommendation was the training database. Build up a heuristic library with case studies. That's what we tried for our place, but you also tried with case studies somewhere else, and maybe we can pull these case studies together. Because case studies is really what drives the research and development. So manufacturers produce prototypes that makes researchers happy in the first before they realize that there are a lot of bugs. Then finally, after years, they might deliver these beautiful case studies, and then they raise attention to authorities, and they support scientists. And finally, the authorities, they subcontract someone, the service providers, and they buy then the equipment from the manufacturers. And then it's worth the effort for the manufacturers. So our wish for growth with industry plays provide prototypes of sound and design software with plugins allow. Important. Well, at the final, this goal is to become the expert group for remote sensing of the seafloor and submarine habitat covering all domains. That needs to be discussed for sure. And I skip over that due to the time. And yeah,